Refraction of light. Experiment to study refraction of light. First, use a wave box and a slit to produce a light wave. Second, direct an incident light to the center O of the semicircular box. Next, observe the light wave. We see that the light wave bends or reflects towards the normal. Next, measure the angle of incidence I and the angle of refraction R. Next, repeat the above procedures for other angles of incident I and measure the corresponding angle of refraction R. Finally, plot a graph of psi I versus psi R. Experimental results shows that when light travels from air to Periscopes, the light wave will bend towards the normal. Also, the graph of psi I against psi R shows that psi I is proportional to psi R. It is a straight line passing through the origin. The ratio psi I over psi R is equal to the slope of the graph, which is a constant value. In experiment, it is equal to about 1.5, where 1.5 is called the refractive index of Periscope. By symbol, refractive index is n. Therefore, we have n equal to psi I over psi R. Example 1. A light wave travels from air into Periscope of refractive index 1.5 and an angle of incidence 50 degrees. Find the angle of refraction R. By n equal to psi I over psi R, we have 1.5 equal to psi 50 degrees over psi R. Therefore, R equal to 30.7 degrees. Example 2. A light wave travels from air to glass of refractive index 1.53. Find the angle of incidence and the angle of refraction. From the diagram, the angle of incidence I equal to 90 degrees minus 30 degrees, which is 60 degrees. Let the angle of refraction be R. By n equal to psi I over psi R, we have 1.53 equal to psi 60 degrees over psi R. Therefore, R equal to 34.5 degrees. Example 3. A light wave travels from air into glass of refractive index 1.52. Find the angle of refraction R and the angle of incidence I. R equal to 90 degrees minus 75 degrees, which is 15 degrees. By n equal to psi I over psi R, we have 1.52 equal to psi I over psi 15 degrees. Therefore, I equal to 23.2 degrees. Example 4. A light wave passes from air into a medium X as shown. find the refractive index of X. From the diagram, this is the normal, I, R. Angle of incident I equal to 90 degree minus 36 degree, which is equal to 54 degree. And angle of refraction R equal to 90 degree minus 58 degree equal to 32 degree. By N equal to psi I over psi R, we have Nx equal to psi 54 degree over psi 32 degree, which is equal to 1.53. Notice that different material or mediums have different refractive index. For air or vacuum, refractive index is 1. For water, refractive index is about 1.33. For Perspex, refractive index is about 1.5. For glass, refractive index is from 1.5 to 1.7. For diamond, the refractive index is about 2.4. Notice that refractive index only depends on the medium, and refractive index does not depend on shape or the mass of the body. Note that air or vacuum has smallest refractive index, N equal to 1. Compared with air, water has greater or higher refractive index. Therefore, air is a less dense medium and water is a denser medium. When light travels from air to water, it bends towards normal. When light travels from a less dense medium, for example, air, to a denser medium, for example, water, it bends towards the normal. What happens when light travels from Perspex to air? First, let's see if light travels from air to Perspex. We have angle of incidence I and angle of refraction R. Refractive index of Perspex N equal to psi I over psi R. However, if the light wave travels from Perspex to air, we have the angles I change to theta A, where theta A is the angle between the light wave and the normal. And the angle of refraction R will change to theta P, where theta P is the angle between the normal and the light wave in Perspex. Therefore, we have N equal to psi theta A over psi theta P. And this formula is very important. Example 5. A wave of light passes from Perspex into air as shown. Find the angle of incidence I and the angle of refraction R. After we draw the normal, we see that we have the light wave travel from Perspex into air, angle of incidence I, and angle of refraction is R. Now we apply the equation N equal to psi theta A over psi theta P. We have refractive index of Perspex is 1.5 equal to psi theta A over psi theta P, where theta P is equal to I, which is equal to 90 degree minus 68 degree, which is equal to 22 degree. Therefore, theta A equal to 34.2 degree. which is equal to angle of refraction, R. Therefore, we have angle of incidence, I, equal to 22 degrees, and angle of refraction, R, equal to 34.2 degrees. Example 6. A wave of light passes from water into air as shown. Find the angle of incidence, I, and angle of refraction, R. From the diagram, after we draw the normal, we have angle of incidence, I, equal to 125 degrees minus 90 degrees, which is equal to 35 degrees. By NW equal to sine theta A over sine theta W, we have 1.33, the refractive index of water, equal to sine theta A over sine theta W, which is equal to 35 degrees. Therefore, theta A equal to 49.7 degrees. And theta A is equal to angle of refraction. Therefore, angle of refraction equal to 49.7 degrees. Example 7. A wave of light passes from a medium X into air as shown. Find the refractive index of X. We have two methods. Method 1, using nx equal to sine theta A over sine theta X. By drawing the normal, we see that theta A equal to 90 degrees minus 25 degrees, which is equal to 65 degrees, and sine theta X equal to 90 degrees minus 60 degrees, which is equal to 30 degrees. Therefore, we have refractive index of X equal to sine 65 degrees over sine 30 degrees, which is equal to 1.81. Method 2. By using reversibility of light, if the light travels from air into X, we have the same path. In this case, the angle of incidence, I, is equal to 65 degrees, and the angle of refraction, R, equal to 30 degrees. Since at this time, the light wave travels from air to X, then we have nx equal to sine I over sine R. This formula can be applied. Therefore, nx equal to sine 65 degrees over sine 30 degrees, which is equal to 1.81. We got the same result. Example 8. A light wave travels from water into air as shown. Given that refractive index of water is 1.33. Find the angle of incidence, I, so that the refracted wave is along the boundary. By applying NW equal to sine theta A over sine theta W, we have 1.33 equal to sine 90 degrees, because theta A is 90 degrees, over sine I, because I is equal to theta W. Therefore, we have sine I equal to 1 over 1.33, implying I equal to 48.8 degrees. Look at, when light travels from water to air, it bends away from normal. Also, when light travels from a denser medium to a less dense medium, for example, from water to air, it bends away from normal. Daily examples about refraction of light. First, the bending of rock in a liquid. Consider a rock PQ put inside a beaker. When water is added, the portion of the rock in the water appears to bend. Explanation: when light waves X and Y from P travels from water into air, they reflect away from normal. When the reflected waves are produced backward, they meet at a point P pi, which is higher than P. The image of the rock immersed in water appears to bend in the way shown. Another example about refraction of light is the shallower of water depth. Consider a point P at a real depth H underwater. When looking from above water, the image of P appears to be higher than its real position. Explanation: consider two light waves from P towards the water surface. Due to refractions from water, which is a denser medium, to air, which is a less dense medium, the light waves will bend or reflect away from normal. By producing the reflected waves backward, they meet at a point P pi, which is above P, and the apparent depth of P, H pi, smaller than H. Since the apparent depth is smaller than the real depth, therefore the water depth appears to be shallower than expected. Total internal reflection. Direct a light wave from the edge of a semicircular glass block towards the center O. When the angle of incident I increases from 0, describe what happens to the light wave. First, when I is small, because n equal to sine theta A over sine theta G, and n refractive index of glass is about 1.5. Therefore, we have theta A larger than theta G. Since angle of incident I equal to theta G, and angle of reflection R equal to theta A. Therefore, we have I is larger than R. As a result, the light wave is reflect or bend away from normal. when I increases from 0, the reflected light becomes stronger and stronger, and the reflected light becomes weaker and weaker. Second, when I increase to a value such that I equal to C, or we say C is called the critical angle. The reflected angle R becomes 90 degrees, and the light wave is reflected along the boundary. Because n equal to sine theta A over sine theta G, and theta G equal to C, and theta A equal to 90 degrees. Therefore, we have n equal to sine 90 degrees over sine C, and sine C equal to 1 over n. Mathematically, the critical angle of the medium C equal to r sine 1 over n. Next, when the angle of incident I increase further such that I is larger than the critical angle C, in this case, total internal reflection occurs, and the light is totally reflected in glass. Notice that the reflected light is as bright as the incident light. In total internal reflections, there will be no reflected light. What are the necessary conditions for total internal reflection? Total internal reflections occurs only when both the light travels from a denser medium to a less dense medium. For example, the light travels from water to air. And the angle of incidence I is greater than the critical angle of the medium. That is I larger than C. When both conditions exist, the light will be totally internal reflected. Example 9. Find the critical angle of the following materials by using sine C equal to 1 over n. For water, we have sine C equal to 1 over 1.33. Therefore, critical angle of water is equal to 48.8 degrees. For Perspex, we have sine C equal to 1 over 1.5. Therefore, critical angle of Perspex equal to 41.8 degrees. Similarly, the refractive index for glass is 1.53. Therefore, sine C equal to 1 over 1.53. Critical angle of glass is 40.8 degree. For diamond, size C equal to 1.2.4. Therefore, critical angle for diamonds equal to 24.6 degree. Example 10. In each of the following cases, explain whether total internal reflections will occur or not. Given critical angle of water is 48 degrees. Case 1. Since the light travels from air to water, which is from a less dense medium to a denser medium, therefore, total internal reflection never occurs. For case 2, the light travels from water to air, which is from a denser medium to a less dense medium. However, the angle of incidence I equal to 90 degree minus 55 degree equal to 35 degree, which is smaller than the critical angle of water. Therefore, total internal reflections does not occur. For case 3, the light wave travels from water to air, which is from a denser medium to a less dense medium. Also, the angle of incidence I equal to 90 degree minus 40 degree, which is 50 degree. Since I is larger than the critical angle of water, therefore, total internal reflections in this case will occur, and the light wave will be totally reflected internally. Example 11. When a light wave is directed to the center of a semicircular glass block, O, the reflected light is along the boundary as shown in the diagram. A. In the diagram, can you mark the critical angle by C? By drawing the normal, the critical angle C can be marked. Next, find the critical angle C equal to 90 degree minus 53 degree, which is equal to 37 degree. Part B. Find the refractive index of glass block. By size C equal to 1 over N, we have N equal to 1 over size C, equal to 1 over size 37 degree. Therefore, refractive index of the glass block equal to 1.66. Example 12. The figure shows the path of a light wave from air into a rectangular block X. A. Find the critical angle of X. From the diagram, the critical angle is C, which is equal to 50 degree. Also, the refractive index of X equal to 1 over size C equal to 1 over size 50 degree equal to 1.31. Part B. Find the angle of incident I. From the diagram, we have angle of reflection R equal to 40 degree by N equal to psi I over psi R. We have 1.31 equal to psi I over psi 40 degree. Therefore, I equal to 57.4 degree. Example 13. An air bubble of center O is inside a liquid. A light wave enters the bubble as shown in the diagram. The refractive index of the liquid is 1.4. Part A. Find the critical angle of the liquid. Psi c equal to 1 over n equal to 1 over 1.4. Therefore, critical angles of the liquid equal to 45.6 degrees. Part B. Explain what would happen to the light wave if theta equal to 35 degrees. If theta equal to 35 degrees, that means angle of incidence I is smaller than the critical angle. Therefore, the light wave will be reflected into the air and bend away from the normal. By symmetry, the light wave will finally reflect into the liquid with angle of refraction equal to 35 degrees. Explain what will happen to the light wave if theta equal to 52 degrees. If theta equal to 52 degrees, then the angle of incidence I will be larger than the critical angle. Therefore, total internal refraction will occur. Example 14. When a small light source S is 2 meters below water, a bright circle is formed on water surface. Given that refractive index of water is 1.33. A. Find a critical angle of water. By psi c equal to 1 over n equal to 1 over 1.33, we have c equal to 48.8 degrees. Part B. Explain why a bright circle is formed on the water surface. Hence, find the radius of the bright circle. When the light from the source travels towards air, it bends away from the normal when the angle of incidence I is smaller than critical angle C. When the angle of incidence I becomes the critical angle, the reflected light will travel along the boundary. By symmetry, there is another light wave traveling at an angle of incidence I equal to C on the other side, with reflected light along the boundary. When seen from above water, there is a bright circle with center O and radius R. Considering the triangle, we have the relation between H and R is tangent C equal to R over H. R equal to H tangent C, which is equal to 2 times tangent 48.8 degrees, which is equal to 2.28 meters. Applications of total internal refraction. The first is periscope. We use two 45, 90 degree, 45 degree glass prisms. In order to direct the light waves in the path zone, we should put two glass prisms in the position zone. The angle of incidence I is equal to 45 degrees. By psi c equal to 1 over n equal to 1 over 1.5, which is the refractive index of glass. Therefore, the critical angle of glass equal to 41.8 degree. Because I equal to 45 degree is larger than the critical angle, which is 41.8 degree. Therefore, total internal reflection occurs. Similarly, at the bottom, the angle of incidence is again equal to 45 degrees, and the light wave is also totally internal reflected. The light wave from the objects will undergo total internal reflection at the surface of the glass 2 times, and the image remains erect, same size as objects. Another application of total internal reflection is light guide by using optical fiber. Optical fibers are made of glass fibers of refractive index C about 1.5, and the critical angle is about 41.8 degree. When a light wave travels through the glass fibers from air, it reflects into the glass fiber. Inside the glass fiber's surface, the angle of incidence is larger than the critical angles of glass. Therefore, total internal reflections occurs inside the fiber. Again, the angle of incidence is also larger than the critical angle. Therefore, we have multiple total internal reflection occurs. Finally, the light wave will reflect into the air from the other side or from the other end of the fiber. In this case, the optical fiber acts as a light guide to guide the light travels inside the tube. Note that optical fibers can also be used in telecommunications. To deliver electrical signals. Another use of total internal reflections is the reflector on the wall. By using 45 degree, 90 degree, 45 degrees glass prism. At night time, the light sent from the car's headlamp will towards the prism and undergo total internal reflections inside the prism. Because I is 45 degree, which is larger than critical angle of glass, which is 41.8 degree, total internal reflections occurs twice inside the glass prism, such that the light wave will be reflected backward towards the drivers. Therefore, the drivers can see the roads ahead clearly. Why diamond is much more sparkle than glass? or we say white diamond is much more brilliant than glass. By psi c equal to 1/n, because refractive index of diamond equal to 2.4, therefore the critical angle for diamond psi c d equal to 1/nd equal to 1/2.4. Therefore, the critical angle for diamond is equal to 24.6 degrees, which is much smaller than that of the critical angle of glass, which is about 41.8 degrees. When a light wave enters from air into the diamond surface, it is reflected towards the bottom surface. Since critical angle of diamond is 24.6 degrees, which is very small, therefore I is larger than critical angle of diamond, and total internal refractions occurs. And the light wave travels to the bottom surface on the other side. Total internal refraction occurs again at this side because I pi is also larger than critical angle of diamond, and the light wave will be reflected to the upper surface. And finally, reflect to air. As a result, most of the light waves going down from above the diamond will undergo total internal refraction and finally reflect upward to air. This explains why diamond is much more sparkle than glass.